Your grandmother told you she could feel the rain coming. Not see it, not hear it on the roof. Feel it in her knee. And everybody smiled, because that is the kind of thing grandmothers say. Nice old lady. Bit superstitious, maybe a little dramatic. Except she was right. She was dead right. And what nobody bothered to ask, what no doctor took seriously for a very long time, was the obvious question, how? How does a storm that has not arrived yet reach inside a woman's knee and turn a dial marked pain? That is a physics question, a real one. And the answer is stranger than you think because it involves gas, pressure, dissolved molecules, and a law written down over 300 years ago by a man named Robert Boyle. Your grandmother's aching knee is a barometer, a genuine functioning pressure instrument made of bone, cartilage, and nerve endings. And today I want to take that instrument apart and show you how it works. Let us begin with what is pressing on you right now. Air. You live at the bottom of an ocean, not water, air. And that ocean has weight. Every square inch of your body right now has about 14.7 pounds of atmosphere stacked on top of it. That is roughly the weight of a bowling ball sitting on every square inch of your skin. Your whole body, if you added it all up, has something like 15 tons of air pressing in on it. 15 tons. And you do not feel a thing. Why not? Because you are not being crushed from one side. The pressure pushes equally from every direction. It pushes on the outside of your chest and it pushes on the inside too. The air inside your lungs, the fluids in your tissues, the gases dissolved in your blood, all of it is at the same pressure as the atmosphere outside. There is a balance, an equilibrium. And when there is equilibrium, you feel nothing. You just walk around at the bottom of an ocean of air without ever noticing the ocean. This is an important idea, so let me make sure it really lands. Imagine you are a deep-sea fish born 1,000 feet below the surface. The water pressure at that depth is enormous, about 30 times what we experience at sea level. But does the fish feel crushed? Of course not. The pressure inside its body matches the pressure outside. It swims around as comfortably as you walk around your kitchen. The fish does not know it is under pressure any more than you know you are under pressure. It is only when the pressure changes, when the balance is disrupted, that things go wrong. Haul that deep-sea fish up to the surface too quickly and the dissolved gas in its blood comes out of solution. The swim bladder overinflates, the eyes bulge, the physics of pressure imbalance tears the animal apart. The same physics, by the way, gives scuba divers the bends if they surface too fast. Nitrogen bubbles in the blood, agony in the joints. Remember that. We are going to come back to it. Good, remember that word, equilibrium. It is going to matter enormously. Now, what happens when a storm rolls in? A low-pressure weather system. That is what a storm front is. The barometric pressure drops. How much? Not a lot. A typical weather front might drop the pressure by, say, 10 to 30 millibars. In terms of everyday numbers, that is a change of about 1 to 3%. 1%. That is tiny. If you were carrying a 100-pound sack, a 1% change means someone took off a single pound. You would hardly notice. So the first clue in our detective story is already a puzzle. The pressure change is absurdly small. 1%, 2%. Nothing dramatic happens to buildings. Your tires do not explode. Your sealed bag of chips from the store does not pop open. The world looks exactly the same. And yet your grandmother's knee screams. A 1 to 3% change in atmospheric pressure, and she knows a storm is coming 12 hours before the first raindrop falls. How? Let us look at the wrong answers first, because a good investigation eliminates suspects before it catches the culprit. Suspect number 1, it is all in her head. This was the medical establishment's favorite theory for a very long time. Joint pain and weather. Coincidence. Confirmation bias. She remembers the times her knee hurt before rain, and she forgets the times it hurt on a sunny Tuesday. Just an old wives' tale. And look, that sounds reasonable. Humans are pattern-matching machines. We see connections everywhere, even where none exist. We see faces in clouds, and intent in coincidence. A few well-timed aches during autumn storms, and Grandma builds a whole theory about it. The brain is very good at constructing narratives from noise. Doctors loved this explanation because it required no mechanism, no physics, no biochemistry, just a cognitive bias with a comforting name. Case closed. Move on. But then researchers started actually testing it, not with surveys, not with anecdotes, with data. A study at Tufts University tracked 200 people with osteoarthritis and matched their daily pain reports to the weather data from the nearest station, some within a single mile of the participant's home, they found a real measurable association between dropping barometric pressure and increasing knee pain. Not imaginary, not placebo, statistical, reproducible, significant. Then came an even bigger study, a citizen science project out of the University of Manchester. They called it, and I love this name, Cloudy with a Chance of Pain. They tracked over 13,000 people across the United Kingdom using a phone application. Daily pain reports, matched with GPS weather data. Over 5 million symptom entries across 15 months. The result? Days with low pressure, high humidity, and strong wind were about 20% more likely to be high pain days. And here is the clincher. Even after they controlled for mood, even after they controlled for physical activity, the weather pain link persisted. It was not that people felt sad on rainy days and reported more pain. The pain was there, independent of their emotional state. Grandma was not imagining things. So suspect 1 is eliminated. It is not purely psychological. Something physical is happening inside the body. Suspect number 2, temperature. Cold makes muscles stiff. Cold thickens the synovial fluid in your joints, the way cold honey moves slower than warm honey. Cold constricts blood vessels in your fingers and toes, reducing circulation and slowing the removal of inflammatory waste products. That is all true, and a lot of stormy weather is also cold weather. So maybe it is the cold doing the damage, not the pressure. A perfectly fair hypothesis. But when the Manchester team pulled the data apart, when they isolated each weather variable independently, temperature by itself did not have a significant independent association with pain, once you controlled for everything else. Humidity did, wind did, and pressure did, even when the temperature had not changed at all. A warm, low-pressure day could still hurt. Cold is a co-conspirator, not the ringleader. It makes a bad day worse, but it does not create the bad day on its own. What about humidity? Damp air, swollen tissues, something about moisture getting into the joints. People say this all the time, and humidity does show up in the data. But humidity alone does not explain why sealed joints that never touch outside air, respond to weather. The moisture is not seeping into your knee through your skin. That is not how joints work. Humidity might affect surface tissues, muscles, mood, but the joint capsule is sealed. Whatever is happening inside that capsule has to obey a different set of rules. So now we have eliminated the easy suspects. The effect is real. It is not just cold, and it is not moisture creeping in from outside. The culprit is pressure, specifically the drop in barometric pressure that precedes bad weather. But we are back to the original puzzle. A shift so small you would need a sensitive instrument to measure it. How does that produce actual pain in a joint? Here is where the physics gets interesting. I need you to think about your knee differently. Forget the anatomy textbook picture for a moment. Forget the tendons and the ligaments and the muscles. Think of your knee as a sealed container, because that is what it is. Every movable joint in your body, your knees, your hips, your shoulders, your knuckles, is enclosed in something called a joint capsule. A tough, fibrous casing sealed around the ends of the bones where they meet. Inside that capsule is synovial fluid. Beautiful stuff. Slippery, viscous, like egg white. Its job is to lubricate the joint so your bones glide smoothly against each other, and to nourish the cartilage that has no blood supply of its own. But that synovial fluid is not just a lubricant. It is a liquid, and like all liquids in your body, it has gases dissolved in it. Nitrogen, oxygen, carbon dioxide. These gases got there from your bloodstream, absorbed from the air you breathe, carried through your circulatory system, and slowly diffusing into every fluid compartment in your body. Right now, those gas molecules are floating around in the synovial fluid of your knee, dissolved and invisible, the same way carbon dioxide is dissolved in an unopened bottle of soda. You do not see any bubbles in a sealed soda bottle, but the gas is there. It is dissolved under pressure, waiting. And that is our first real clue. Dissolved gas in a sealed container, under pressure. Now, here is Robert Boyle walking on stage 300 years before your grandmother was born. Boyle's Law, 1662. If you have a gas in a closed container and you keep the temperature constant, the pressure times the volume equals a constant. P times V equals K. That is it. Simple. Beautiful. And it means this. If the pressure goes down, the volume goes up. Squeeze a gas and it shrinks. Release the squeeze and it expands. You see this every time you fly in an airplane. You get on the plane with a half-empty water bottle. The cabin pressurizes, but not all the way. The pressure at cruising altitude is about 80% of what it was on the ground, a 20% drop. And what happens to that water bottle? It puffs up. The air trapped in the sealed space above the water expands until the bottle is taut like a drum. Same amount of gas, lower external pressure, greater volume. Boyle's law, working right in front of your eyes at 35,000 feet. Your ears do the same thing. The gas in your middle ear pushes your eardrum outward until you swallow to equalize. But what if you could not equalize? What if the space was sealed and stiff? That uncomfortable pop would become pain. Apply this to your knee. The atmospheric pressure outside your body is part of the squeezing force that keeps everything compact. When the barometric pressure drops by, say, 2%, the outward pressure on your knee joint decreases. The gases inside the joint are now at a slightly higher relative pressure compared to the outside. So what do? They expand. Just a little. 2% pressure drop. Roughly 2% expansion of any gas volumes. 2%, that is nothing, right? You would never feel that. Hold on. Do not close the case yet. We have another law to consult. A man named William Henry, working about 140 years after Boyle, figured out something about dissolved gases. Henry's law says this: the amount of gas that stays dissolved in a liquid is proportional to the pressure above that liquid. Higher pressure, more gas stays dissolved. Lower pressure, gas starts to come out of solution. Think about the soda bottle again. While the cap is on, the carbon dioxide stays dissolved. High pressure above the liquid, gas stays put. You twist the cap, pressure drops, and immediately bubbles form. Gas that was invisible, dissolved, completely hidden in the liquid, suddenly nucleates into visible bubbles and starts expanding. The soda was always full of carbon dioxide. You just could not see it until the pressure balance changed. Now here is where the two laws gang up on your knee. Boyle's law says existing gas pockets get bigger when external pressure drops. Henry's law says dissolved gas that was previously invisible comes out of solution and forms new gas pockets. Both effects happen simultaneously. Both are driven by the same trigger, the barometric pressure falling as a storm system approaches. You already knew this kind of thing could happen in joints, by the way. You have heard the evidence yourself. Crack your knuckles and what you hear is cavitation. When you pull the joint surfaces apart, you create a local pressure drop inside the synovial capsule. Dissolved gas, mostly nitrogen and carbon dioxide, rushes out of solution and forms a bubble so fast that it makes an audible pop. X-ray the joint right after, and you can actually see the gas bubble sitting there, taking up about 15 to 20% of the joint volume. It takes roughly 20 minutes for that gas to redissolve into the fluid, which is why you cannot crack the same knuckle again right away. The gas is real. It is always there, dissolved and waiting. And it responds to pressure changes with surprising eagerness. So we have two mechanisms working in concert. Boyle's law is expanding any existing gas pockets. Henry's law is pulling new gas out of hiding. Together they produce a slight increase in volume inside the sealed joint capsule. But I said very slight, I keep saying it. A micro-expansion, and you are right to be skeptical. In a healthy knee, this should not matter at all. The joint capsule is elastic, it stretches. The synovial membrane is flexible. A tiny increase in internal volume, a few microbubbles. The healthy joint just accommodates it and moves on. You feel nothing. A young person with healthy knees walks through a thunderstorm and never notices a thing. So why does grandma feel it? This is the real answer. This is where the detective story pays off. The issue is not the size of the pressure change. The issue is what has happened to the joint before the storm ever arrives. Grandma has arthritis. Her knee has been degraded by years of wear or inflammation or both. In an arthritic joint, the cartilage that cushions the bone ends is worn thin or gone entirely. The synovial membrane is inflamed and thickened. The joint capsule is stiffened by chronic swelling. The space inside the joint is already reduced, already under strain. And here is the critical part. The nerve endings in and around that joint are sensitized. Inflammation does not just cause swelling. It lowers the threshold of pain receptors. Nerves that normally require a strong signal to fire are now on a hair trigger. They are waiting for a provocation that in a healthy joint would be utterly ignorable. Into this environment, a 2% pressure drop sends a wave of microexpansion. Gas volumes grow. Dissolved gas nucleates into new bubbles. The tissues which in a healthy joint would stretch and accommodate cannot stretch. They are stiff. They are swollen. There is no room. The expansion, tiny as it is, presses outward against a capsule that refuses to give. That capsule is lined with mechanoreceptors, pressure-sensing nerve endings, and those nerve endings are already inflamed, already sensitized, already poised at the edge of firing. Researchers at Tufts University demonstrated something remarkable that shows just how physical this effect is. They took a cadaver hip joint, a real human hip, and measured what happened to the ball and socket fit when they dropped the barometric pressure. The ball of the femur shifted about 1/3 of an inch off its normal track. 1/3 of an inch. In a cadaver with no muscles, no nervous system, no psychology of any kind. Just bones, cartilage, and physics. The pressure change physically moved the joint. In a living person with arthritis, where that space is already compromised and those nerves are already raw, that shift is not subtle. It is an alarm bell. A 1% expansion in a joint with no room to give, pressing against nerves that are already screaming. That is the mechanism. It is not that the pressure change is large. It is that the system is primed to detect it. Think of it this way. Imagine you have a room full of people, and one more person walks in. If the room is a gymnasium, nobody notices. Plenty of space. People shuffle slightly, and that is the end of it. If the room is a packed elevator, one more body changes everything. Elbows and ribs. Somebody steps on your foot. Somebody else's bag is pressing into your side. The addition is the same. One person, but the response depends entirely on how much room was already there. A gymnasium absorbs the newcomer. An elevator amplifies them. Arthritis turns your knee into a packed elevator, and the barometric pressure drop is that one extra person squeezing in. There is something even more beautiful about this if you think about it carefully. The body is not just passively receiving the pressure change. The joint is actively detecting it. Those mechanoreceptors in the capsule are doing their job. They exist to sense pressure and stretch. In a healthy joint, the tiny signal gets processed and filtered out. It is below the noise threshold. The brain ignores it. But in an inflamed joint, the signal arrives amplified, passed through sensitized nerve pathways, and the brain interprets it as pain. The joint is functioning as a detector. It is sensing a real physical change in the environment. Grandma is not superstitious. She is well calibrated. And the timing makes sense too. Barometric pressure starts dropping hours before a storm actually arrives. The front is still miles away. The rain has not started. The sky might still look clear, but the pressure is already falling. The gases in her knee are already responding. By the time the first drops of rain hit the window, her knee has been telling her about the storm for 6, 8, maybe 12 hours. She is not predicting the weather, she is measuring it. In real time, faster in some cases than the weather broadcast. The speed of the pressure change matters too. Researchers noticed that a sudden drop, the kind that comes with a fast-moving front, hurts more than a gradual decline. That fits the physics perfectly. A sudden pressure drop means the gas expansion happens quickly, faster than the body's mechanisms for slowly equalizing pressure across tissues. A gradual drop gives the system time to adjust. Blood flow carries dissolved gas away. Tissues relax incrementally, but a sharp drop overwhelms the equalization rate, and the imbalance peaks before the body can catch up. It is the same reason you get the bends from a fast ascent but not a slow one. The physics of dissolved gas does not care about your comfort. It cares about rates. Now I want you to appreciate how many layers of physics are stacked inside this one phenomenon. You have got fluid mechanics, the behavior of synovial fluid under varying conditions. You have got gas laws, both Boyle and Henry, governing how trapped and dissolved gases respond to external pressure changes. You have got material science, the compliance and stiffness of biological tissues under chronic inflammation. You have got neuroscience, the sensitization of nerve receptors through inflammatory signaling. And you have got atmospheric physics, the pressure variations driven by large-scale weather systems, hundreds of miles wide, all of it converging on one woman's knee. 5 different branches of science, developed independently over centuries by people who never met each other, and they all intersect at the same point. That is what I love about physics. You start with something that sounds like folk wisdom, an old lady saying her knee hurts before rain, and when you pull it apart, you find layer after layer of real deep science. Boyle never thought about arthritis. Henry never thought about knees. The atmospheric scientists studying pressure fronts were not thinking about synovial fluid, but their laws, written down across 3 centuries, describe exactly what is happening inside a joint capsule when the barometer falls. And this raises interesting questions that I want to leave you with because they have no clean answers yet. We know the mechanism in broad strokes. Pressure drops, gas expands, sensitized nerves fire, but the details are still being worked out. Why do some people with arthritis feel the weather strongly, while others with the same condition feel nothing? The Manchester study found enormous individual variation. Some participants tracked perfectly with pressure drops. Their pain charts looked like mirror images of the barometric readings. Others showed no pattern at all. Is it the specific type of joint damage, the degree of nerve sensitization, genetic differences in how pain signals get processed or filtered, perhaps differences in the gas composition of their synovial fluid? We do not fully know. The investigation is not over. There is also the question of whether this mechanism extends beyond joints. People report that old bone fractures ache before storms. Surgical scars tighten. Amputees feel phantom pain in limbs that are no longer there when the weather shifts. Migraine sufferers track with low-pressure systems. Are the same gas and tissue mechanics at work in all of these? The physics would suggest similar principles. Scar tissue is stiff, poorly vascularized, packed with disorganized nerve endings. It is another packed elevator. But nobody has done the full controlled studies across all these different tissues and conditions to prove it conclusively. The folk knowledge is centuries old. The physics is clear. The biology is still catching up. What we can say is this: the human body is not a sealed, rigid machine insulated from the atmosphere. It is permeable to pressure. That every joint capsule, every pocket of dissolved gas, every compliant membrane is in constant quiet dialogue with the 14.7 pounds per square inch of air above it. Most of the time the equilibrium holds, and you feel nothing. But when the system is compromised, when inflammation has stiffened the tissues and primed the nerves, the body becomes sensitive to variations so small that no instrument on your shelf would bother reporting them. A 1% change, less than 1 inch of mercury on a barometer. Your grandmother's knee picks it up before the weatherman does. There is a lesson in that. Not about joints, really, but about detection. The best detectors in the world are not the ones with the most powerful amplifiers. They are the ones where the noise floor is lowest. A healthy knee has a high noise floor, too much flexibility, too much cushioning, too many layers of dampening between the stimulus and the nerve. The tiny pressure signal disappears in the noise, drowned out by the elasticity of healthy cartilage and the compliance of a relaxed capsule. The brain ignores it the way you ignore the hum of a refrigerator in the background. An arthritic knee has had its cushioning stripped away. The cartilage is thin or gone, the capsule is rigid, the noise floor drops, and suddenly a signal that was always there, that was always physically real, becomes detectable. It rises above the threshold. It is the same principle behind the most sensitive physics experiments in history. You do not make a detector better by making the signal louder. You make it better by removing everything that is not the signal. When we build gravitational wave detectors, we do not try to make the waves bigger. We cannot. We remove every possible source of vibration, every thermal fluctuation, every acoustic disturbance, until the detector is quiet enough to hear space-time ripple. Your grandmother's arthritis, cruel as it is, did exactly that to her knee. It stripped out the cushioning and turned the joint into one of the most sensitive barometers in the house. She did not gain a new ability. She lost the padding that was hiding an ability she always had. So the next time someone tells you they can feel the rain coming in their bones, do not smile politely. Ask them how far out the front is. Ask them if the pressure is dropping fast or slow, because the physics says they might actually know. Their body is a measuring instrument. And 300 years of gas laws are written into every ache. What I would like to know from you is this: have you ever noticed a pattern in your own body? Some ache or stiffness or strange sensation that seemed to track with something in the environment? And if so, what do you think the mechanism might be? Think about it, because the answer might be more interesting than you expect.